All right, the next topic we need to discuss is dimensional analysis, and this is the process by which somebody changes one unit to another. You might do that if you're trying to convert from inches to centimeters or centimeters to inches or pounds to kilograms, something like that. The process of doing it is called dimensional analysis. There's a table on page 12 in your book, table R4, English to metric equivalence, that has length, mass, and volume conversion factors. And there's only very few of them in there. There's also one in the back of your book. The back cover on the inside has a ton of different conversion factors for SI units, and so you might want to look at that. Let me write that in. Now, unit factors are essentially conversion factors of the same thing. For example, 1 inch is 2.54 centimeters. If I take 1 and I divide it by 2.54, it does not equal 1. But the unit of measure, or the length, I should say, 1 inch, is the same as 2.54 centimeters. So if I was to divide up 2.54 centimeters in how many inches it takes to go into that, you would say 1. Or if I was to take 1 inch and divide it by the amount of centimeters that it takes to make that inch, it would be 2.54 centimeters. If I take one piece of something that is 1 inch long and I divide it, or if I cut it into the number of pieces that it takes to have a length of 2.54 centimeters, it would be the exact same length, so it would just be one of those pieces cut into itself. So you wouldn't cut it at all, really, but it would still be 1. These are unit factors. Anytime the measurement is the same, but with different units, we call those unit factors. Unit factors are used to convert from one unit to another, since by definition the two measurements, although different in units, are equivalent in value. We have some examples of problems to do here. Problem 1, a pencil is 7 inches long. What is that length in centimeters? Well, the conversion factor is 1 inch equals 2.54 centimeters. So if I have 7.00 inches, I'm going to use that conversion factor to get the answer, and I call this the box method. I start with 7 inches, the measurement I am given in the top left. Now I have to use the conversion factor in there. I want to cancel out the inches. So I'm going to take that and put it down below, 1 inch. The other number, the 2.54 centimeters, is going to go above it, 2.54 centimeters. Now, you've got inches on the top, inches on the bottom. Those two are going to cancel out, leaving you with just centimeters. 7 times 2.54 is equal to 17.78 centimeters. Now, your number there is 7 inches, has 3 significant figures, and you've got 2.54 centimeters, which has 3, and 1 inch, which has 1. So you might say the answer's got 1 significant figure. Oh, so, okay, we'll have 20 centimeters, and the 0 is not significant. However, that would be wrong. Don't do that. Conversion factors have infinitely many significant figures because we say it is a known fact. So although the 7 has 3 significant figures, both of them have infinite. So your answer has to be to 3 significant figures. So 1, 2, 3, and then we look at the 8 next to it. It's bigger than 5, so that makes this 17.8 centimeters. All right, and the next one, number 2 there, says a student has entered into a 10-kilometer run. How long is this run in miles? Well, there are different conversion factors you can use, and if we were to just use the same one we had in problem 1, we could say that again, 1 inch is equal to 2.54 centimeters. The problem is that we have to go from centimeters to kilometers, and we have to go from inches to miles. So that's a pretty long process. So either way, I'm going to start with 10 kilometers. And because that's the measured distance, and then I have to go from kilometers to centimeters. So there are 1,000 meters in 1 kilometer, and there are 100 centimeters in 1 meter. So you have to do both of those. The kilometers are what we need to cancel out, so that goes down here. Cancel, cancel. 1 kilometer, 1,000 meters goes right there. But now we need to cancel out the meters, so we put the meters in the bottom and 100 centimeters right there. Meters cancel out. Now we want to go from centimeters to inches. So we want to cancel out centimeters. So that goes on the bottom, the 2.54. And you got 1 inch right there. Centimeters cancel out. We're left with inches. We've got 12 inches equals 1 foot. And also we have 5,280 feet is equal to 1 mile. You may or may not remember that number, but that's how many feet are in a mile. So we're going to take the feet and put them below, so 5,280 feet and 1 mile. Feet cancel out, and you're left with simply how many miles are in 10 kilometers. So the way to look at this is everything in the numerator of a problem like this, and the top parts are the numerator. Those numbers are going to multiply together. Everything in the denominator is going to multiply together. And so this would be written as such. I would do 10 times 1,000 times 100 times 1 times 1 times 1 all over 1 times 2.54 times 12 times 5,280. And when you do that, you get 1,000,000, and we can't forget the units, miles, divided by the product of 2.54 times 12 times 5,280 is 160,934.4. And when you take 1,000,000 and divide it by that 160,934.4, you get 6.21 yada 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 miles. Now the problem had 3 significant figures, and if you can see it here, there's that 10 kilometers, 10.0, so it's 3 significant figures. So it's actually 6.213 miles, which rounds it to 6.21 miles. All right, and now that was just problem 2. So let me delete all of these. And go back to here. The speed limit on I-20 is 70 miles per hour. How fast is this in kilometers per hour? Well, we just determined essentially that 10 kilometers is equal to 6.21 miles. All right, and so we have a conversion factor that we already found, but we could use the same thing. And so we can convert miles per hour to kilometers per hour by saying, okay, we've got 70 miles, and here you've got a division per hour, and we're going to convert miles to kilometers by just taking the conversion factor above. 6.21 miles down below, the miles will cancel out, and then 10.0 kilometers above, and that's it. So 70 times 10 is 700 over 6.21, and if you do that, 700 divided by 6.21 is equal to 112.65 kilometers per hour. And here we've got 70 miles per hour. Technically, it would be infinitely many significant figures because a speed limit is a known number. It's not 70.0, it's just 70. It's not one significant figure, even though there's a 0 there or whatever, because again, it's a known value, so it's infinitely many, which means in really the calculator I have has 112.65408. I just couldn't fit it in there. Any number you give is actually fine. If you want to leave it at 2, because, okay, 70 has 2 digits there, this would round to 110 kilometers per hour. If you wanted it to be 1, then it would just be 100 kilometers per hour. But questions like that with this ambiguity won't be given on a test because that would be impossible for you to do. So you're not going to have to worry about that on your test. Now, the final problem here says if there are 365 days in a year, how many seconds are in a year? So we all know these conversion factors, but 365 days, that's where we start. We're going to have to convert days to hours, and there's 24 hours in a day. Days cancel out. Then we need to convert hours to minutes, and there are 60 minutes in an hour. Hours cancel. And then there's 60 seconds in a minute, and your minutes cancel out. So what we end up with is 365 times 24 times 60 squared, and that comes out to 31,536,000 seconds, which is obviously a lot of seconds. Now, 365 days is a number that we can count. So it has infinitely many significant figures. So this is your correct answer. Next topic here is converting the following units. We've got first there 15 cubic centimeters into liters. These are all metric, so it's a little easier, but you need to know in this case that 1 cubic centimeter is equal to 1 milliliter. And so, therefore, there's our 1,000 milliliters in 1 liter. And you can find this, you have the base unit is a liter, and you've got milli, which means that there's 1,000 of them, not a million. But you can go back to the earlier slide in there and see that all those conversion factors within the metric system. And so you have 15 cubic centimeters times 1 milliliter per 1 cubic centimeter. Those cancel out. And then you're going to multiply that by 1,000 milliliters per liter. And the milliliters will go on the denominator so that they cancel out. And you're left with just liters right there. And now you have 15 divided by 1,000. Liters. This comes out to 0.015 liters. And that is your answer. All right, the next problem there is 7.38 grams into kilograms. So 7.38 grams is what we're going to start with to kilograms. There are 1,000 grams in 1 kilogram. So we're going to put the grams below and the kilograms above. We're going to do the same thing here. We're going to divide by 1,000. Another way to look at these problems is to say I've got 7.38. Since I'm dividing it by 1,000, I need to move the decimal place 3 times. So that 1, 2, 3 gives us that number right there, 0.00738, and the grams cancel out, so we're left with kilograms. Or you could do it the way I did in the earlier problem. Now, next one there, 6.7 seconds into milliseconds. The first two examples, we went from a small unit of measure to a larger unit of measure, and the number got smaller. Here we're going from a larger unit of measure to a smaller unit of measure, so the answer should get bigger. So 6.7 seconds, and we have 1,000 milliseconds equaling 1 second. So 1 second goes down there, and 1,000 goes above in the numerator, and so you get 6,700 seconds. You might be asking yourself, scientific notation. So in this case, you would have 6.7 times 10 to the third seconds. How many times does it take to move the decimal to get to being after the first number? So 1, 2, 3. And since it's a number bigger than 1, it's a positive 3. The other numbers, I should go back to those. We had 0.015 liters. In scientific notation, that would be 1.5 times 10 to the negative second liters, because there are 2 zeros in front. And we also had 0.00738 kilograms. In scientific notation, that would be 7.38 times 10 to the negative third kilogram. 3 because we got 3 zeros, and negative because this is a number that is smaller than 1. Next one there is 94.5 grams to micrograms. So what you do is you need to know that there are 1,000,000 micrograms in 1 gram, or you could say 10 to the 6th micrograms is equal to 1 gram. And then you would take 94.5 grams, and you're going to use these conversion factors. You could use 1 gram here and 1,000,000 micrograms above, because the grams cancel out, and you're left with 94.5 million micrograms, or 9.45 times 10 to the 7th micrograms. 1, 2, 3, 4, 5, 6, 7 times you have to move the decimal place, so 10 to the 7th. You could also, there's many ways you could write it. I'm not going to go through them all, but these are the simplest ways to do it, I'll just say. Now, next problem there is 0.073 centimeters into micrometers. Now, all of the previous examples used a base unit at some point, and in this problem, neither unit is the base unit. So we have centimeters and micrometers. So there's 2 ways you could do it. You could go from centimeters into micrometers directly, if you somehow know it, or you could go from centimeters into meters, and then from meters into centimeters. So what I would say is that you have 100 centimeters in 1 meter, and you've got 1,000,000 micrometers in 1 meter. Since we're going from centimeters into micrometers, we're really going to be dividing by centimeters first. So that 100 is actually going to be in the denominator. We would then be going from meters to micrometers, which would be multiplying. So if you combine these two together, you end up with 1,000,000 divided by 100. And you've got 1, 2, and 1, 2. Those cancel out. And then you've got 4 zeros there. That equals 10,000. So what that actually tells us is we have a new conversion factor, is that there are 10,000 micrometers in 1 centimeter. Centimeters cancel out, and that gives you 730 micrometers. So you could, the actual calculation, you could do it in 1 step if you have some other prior knowledge. Now, there's scientific notation. You might look back at that previous slide and see that there's 10 to the 6th micrometers in a meter. There are 10 to the 2nd centimeters in a meter. And you can do the same thing. There's 10 to the 6th divided by 10 squared instead of 1,000,000 divided by 100. And this will be 10 to the 6th minus 2, which is 10 to the 4th, which is 10,000, but you could use that. And so 0.073 centimeters times 10 to the 4th micrometers per centimeter means you need to move the decimal place 4 times. 1, 2, 3, and then it would be a 4. So 730 micrometers. All right, and then the last problem on this page, we've got 7.21 grams per cubic centimeter, converting it into kilograms per cubic meter. And this is definitely one of the most challenging problems. So it's going to require a bunch of space. You have 7.21 grams per 1 cubic centimeter. Now, you're going to need to convert grams into kilograms, and that's the easiest thing to do first. There are 1,000 grams in a kilogram. Or you could say 10 to the 3rd grams is 1 kilogram. So I'm going to put the grams down here. And they cancel out. But now we need to convert cubic centimeters into cubic meters. So X number of cubic centimeters equals Y number of cubic meters. Trying to find out those. Now, I could tell you there's 100 centimeters in 1 meter. And that would be great. So let's put that in. Let's say 10 squared centimeters is 1 meter. I want to get rid of the cubic centimeters down there. So that 10 squared is going to go up here. Now, we have centimeters above and centimeter below. But that only cancels out one of the 3 centimeters. So now we're left with centimeters squared. And we just continue to do the same thing. And so that leaves you with this really long equation of 7.21 times 10 squared times 10 squared times 10 squared kilograms divided by 10 to the 3rd cubic meters. Meters times meters times meters is cubic meters. And so this ends up being 7.21 times 10 to the 6th kilograms divided by 10 to the 3rd cubic meters. The 6 and the 3 will cancel out to leave a 3 there. So this is 7.21 times 10 to the 3rd kilograms per cubic meter. And that is the answer to this question. But just as, if I want to go back a little bit, just to show everything, 10 squared is cubed in the top here. So this is 10 to the 2 times 3, which is 10 to the 6th, okay? And then, when you're canceling out, 10 to the 6th divided by 10 to the 3rd is 10 to the 6th minus 3, which is 10 to the 3rd. So these are old rules of exponential numbers. So you end up with 7.21 times 10 to the 3rd, and the number should be bigger than you would expect because we're increasing the size of the volume by 1,000,000. If you have a yardstick at home or a meter stick, compare 1 centimeter in length to a meter, and in your head visualize the volume that a cubic centimeter takes up compared to a cubic meter. It's not 1,000, it's not 100, it's 1,000,000 times. 1,000,000 little cubic centimeter blocks would go into a cubic meter. And then there's only a difference of 1,000 for kilograms to grams, so we end up with a difference of 1,000. You have to be careful in these problems where you have cubic or square units. If you don't repeat the process like done here 3 times, because it was cubic centimeters, you will get the wrong number. So make sure you're always looking at that. So that's it for the conversion factors and dimensional analysis, at least explicitly at this point. Section R6 is on temperature. And obviously there are 3 temperature scales that are used primarily in this world: Fahrenheit, Celsius, and Kelvin. The Fahrenheit scale is used in America and like 3 Caribbean islands, I think. And so why do we use it? I guess it's just because we're stubborn. But regardless, we use it here in America, so it needs to be discussed. But the scientific community does not use it. It uses Celsius and it uses Kelvin. And you can look at this picture there, and you can see the relationship between all 3 of these temperatures. So 0 Kelvin is called absolute zero. That's the lowest possible temperature. In Fahrenheit, it's negative 460. In Celsius, the one that matters, it's negative 273 degrees. Technically, it's 273.15 below 0 Celsius. Now, what's interesting is if you go up from 0 Kelvin to 273.15 Kelvin, you get 0 degrees Celsius. That's an increase of 273.15 in Kelvin and an increase in 273.15 in degrees Celsius. But in Fahrenheit, it is not a 273.15 difference. And likewise, if you're going from 18 below 0 in Celsius to 0 degrees Celsius, that is a difference of 18 degrees, but in Fahrenheit, it's a difference of 32 degrees for the same temperatures, the freezing point of water to 0 degrees Fahrenheit. So the Fahrenheit and Celsius scales are not the same change in energy, essentially, per unit of measure. But in Celsius and Kelvin, each gradation is the same. So the difference in energy of a degree Celsius is the same as the difference in energy of a Kelvin. And that was done intentionally to make things easier for the whole world that used Celsius once they realized Celsius was not going to work. And we'll see why much later on at the end of the semester when we go over the gas laws, the reason why Celsius fails to be used properly in this class or even a physics class. Suffice it to say that when these are used in actual calculations that chemists use, it fails to work, but Kelvin works. And the reason is that Kelvin is an absolute scale, meaning there's no negatives. That's why we call it absolute zero at 0 Kelvin. Like you can't measure the mass of anything in negative grams. You couldn't measure a negative volume. You couldn't measure a negative number of centimeters for the length of an object. You either have energy or you don't. And temperature is a measurement of energy. You can't have negative energy. You can only have energy or none. So that's why the Kelvin scale works. But we'll see it in actual, like a proof form of that in chapter 8. And you can see the boiling point of water in Celsius is 100 degrees, 273.15 but plus 100 is 373.15. So it's always staying the same. We do have these conversion factors to go between the different temperature measurements, but I will say that anything including Fahrenheit is not going to exist in your test. So these two, although it might be in homework problems, will not be on the test. You will need to know how to convert from Celsius to Kelvin and from Kelvin to Celsius. And you just follow those equations there. So problem number 1, what is body temperature in degrees Celsius and what is it in Kelvin? Well, we should all know that body temperature in Fahrenheit is 98.6 degrees Fahrenheit. So you're going to start with 98.6 degrees Fahrenheit, and the first step is to subtract 32 degrees Fahrenheit from that. And then you will multiply by 5 degrees Celsius for every 9 degrees Fahrenheit. And you'll see that the degrees Fahrenheit cancel out here. Since these are the same, they come out to one number, and they cancel out with the degrees Fahrenheit there. That gives you 37 degrees Celsius. To put that into Kelvin, you just add, so I'll circle that, you add 37 degrees Celsius plus 273.15. Now in reality, it's 37 degrees Celsius times 1 Kelvin per 1 degrees Celsius plus 273.15 Kelvin. But we can just simply take the number in Celsius and add 273.15 to it, and you get 310.15 Kelvin. And there's your body temperature in Kelvin. Next problem here says, what is the boiling point of water in degrees Celsius and in kelvins? So you probably all know that the boiling point of water is 100 degrees Celsius. If you don't know, the boiling point of water in Fahrenheit is 212 degrees. So we already got that, because I feel like you should know that, and I wrote it in there. But in Kelvin, you're just going to take 100 plus 273.15, and you get 373.15. Question 3 there. At what point are Fahrenheit and degrees Celsius equivalent? And this is a tough problem, but basically you just need to combine the two equations from before. And so you could say temperature in Celsius is equal to the temperature in Fahrenheit minus 32 times 5/9. Okay. And so if the temperature in Celsius equals the temperature in Fahrenheit, then I can substitute one of those into this equation, and we would get Tc equals Tc, or you could have Tf equals Tf minus 32 times 5/9, and 32 times 5/9 is 17.7 repeating. So you'd have Tc equals 5/9 Tc because it's this times that, and then times that. So you get 5/9 TC minus 17.7 equals TC. If I move that over there, I get, I would get 4/9 TC equals negative 17.7. Multiply each side by 9 and then divide by 4. And you get negative 40 degrees Celsius. So that means negative 40 degrees Fahrenheit equals negative 40 degrees Celsius. All right, now we're into the section R7, which is on density. Density, which has the symbol rho right there, R-H-O, Greek letter, and it's a lowercase, is the amount of mass an object contains per unit of volume. So you can see its equation right here. Rho is equal to m over v. So if we're looking at SI units of measure, mass is measured in kilograms, and volume is measured in cubic meters. Now, that doesn't really get used that often in chemistry. If it's a liquid, we're going to use most likely grams per milliliter. Or if it's a gas, it's a gram per liter. And if it's a solid, I don't know, it could be kilograms per cubic meter. It could be grams per cubic centimeter as well. It just depends. Now I got a couple of videos here that show and demonstrate how density can be used. So let me just show those. So this picture here just shows you how many different substances have different densities, and if they don't interact with each other, you can just have them all float on top. So like at the bottom of this cylinder, there's honey, which would make it the most dense substance in that cylinder, followed by corn syrup, maple syrup, milk, dish soap, water, vegetable oil, rubbing alcohol, and lamp oil. Now, you could probably mix together the honey and the two syrups and the milk even and get them to mix, but they're very viscous. If you pour them in gently, they probably won't mix. So that's how I've done this before. That's how that would be made. And you can do that. And you can see there's a bolt right in there that's sinking to the bottom because it's not dissolved in there, and it's more dense even than the honey. And then the milk being probably much less viscous than the syrup. If you pour that gently on top, it wouldn't dissolve in it. The dish soap is more viscous than the milk, but less dense than it, so it floats on top, but you can actually get it to sit on top. Again, you have to be very careful and to not disturb the milk as you're slowly pouring the dish soap in. And then even water can sit on top of the dish soap, which is pretty crazy. But if you take Dawn dish soap and you have it in a cup and you slowly, drop by drop, add water to it, it will just sit on top. And then above the water, you've got vegetable oil, which will not dissolve in the water at all. Rubbing alcohol won't dissolve in the oil because it is polar and the vegetable oil is not. And so it's less dense than the vegetable oil, and again, it floats on top. And then above that is lamp oil, which another oil will not dissolve in the rubbing alcohol. All right, and then the last slide here on density has two problems. It says a copper penny has a mass of 3.1 grams and a volume of 0.35 cubic centimeters. What is its density? So let me move that up here. And we've got a mass. I always like to write everything I'm given. It helps organize it, and it makes things more clear when you're trying to do the problem. You have mass 3.1 grams. The volume is 0.35 cubic centimeters. That's a C, not an E. Okay. And your equation is this right here. What we're solving for is the density, so we just can directly use that. And so your density rho is m over v, and we're going to have 3.1 grams, and we're going to divide that by 0.35 cubic centimeters. And if you do the math, you will get a number that is approximately 8.8. It's actually, if you do it in your calculator, you get 8.8571 grams per cubic centimeter. Now, when you're doing these problems, you need to really look at the numbers you're given. 3.1 has two significant figures, and 0.35 has two significant figures. So your answer has to be to two significant figures. So you're going to look at these two numbers here and look to the number right of that, and you have a 5. So that's going to make this round to 8.9 grams per cubic centimeter for problem 1. And that is for copper. Now, let's delete all of this. We can do problem 2 there, which says, what is the volume of a pure silver coin that has a mass of 14 grams and a known density of 10.5 grams per cubic centimeter? So move that back up. And so what we have here, it says what volume. So what you could do is take that equation and rewrite it to solve for volume. So volume is going to be equal to the mass divided by the density. And you can get that by moving the volume over here, moving the density over there. Or if you want to look at it another way, you could think about it as multiplying both sides by volume. So you'd get rho v equals m, and then dividing each side by rho, and you'd get m over rho. And so your volume is the mass divided by the density. All right, so let's do the problem now. Just use the numbers you're given. You have 14 grams, and you're dividing it by 10.5 grams per cubic centimeter. And when you do that, you get 1.3 with repeating, and this is going to be cubic centimeters. Now, the units are going to cancel out. Grams divided by grams cancels out. And what you end up with would be technically 1 divided by 1 over a cubic centimeter. So you could rewrite it like this. And you might remember from math that when you're dividing by a fraction, as we have over here, you can simplify this by flipping the fraction and multiplying it instead of dividing it. So that really becomes 1 times centimeters cubed over 1. And anything divided by 1 is itself, and anything times 1 is itself. So this really just becomes cubic centimeters. Now, the other thing to look at is significant figures. We've got 2 on the 14 and 3 on the 10.5. Since this is a multiplication type step, we're going to have 2 significant figures, not 3. And so the answer is just 1.3 cubic centimeters.